In this lesson, we're going to do 2 pages of notes, and the first page of notes we have here is really looking at field comparisons, and as I have here, put down MC, multiple choice concept questions, often, and I just don't want you to have to think too much about what's similar, what's different about the fields, so I wanted it explicitly in the notes, and I don't think it hurts to show how we have identical, so please make sure you get this in. This is one of the most important things. We have identical magnetic fields in the permanent magnet, the ferromagnets, and our solenoids, or our electromagnet. So for the solenoid, just to remind you, we have moving Q's make B field, right? Moving Q's make B field, and the moving Q's come from the current. So the current is coming through, and when we do our IDL cross R hats, or spin our fingers and stick our thumb out, we get the north pole, so the magnetic field comes out of north into south. It's uniform in the center, just like it's uniform in the center of the permanent magnet. The magnetic field lines do not begin or end. They come out of north back to south. They always wrap on each other, so B fields have no start or end points, so make sure you just get get this into your notes so you can quickly review. Magnetic fields, unlike electric fields, also cannot have isolated poles, right? We have a north pole and a south pole, but you can't cut off the north pole and just keep the north pole the same way. You can isolate a proton and have a positive charge, right? And you can isolate an electron and have a negative charge, and of course the field lines do begin and end, so they don't just go through. They begin on positive, right? And they end on negative. So start and end points, we do have isolated charge poles. And the last thing that I want you to get into your notes is the energy storage. We will see in our next chapter, when we do Faraday's law and induction, that it becomes very important for us to understand that the magnetic field does store energy. That energy can be utilized by letting the magnetic field change, and talk about the time rate of change of the magnetic field. But for right now, just get in here that the magnetic field does store energy. That energy will only be stored as long as the magnetic field is present, so as long as the current is running. And so it is not a long-term storage device. So the energy in a capacitor is a long-term storage device because we can store the energy, charge the capacitor, and just let it sit. So please make sure you get all of these annotations. And now we are going to look at one final device called the toroid, or El Toroid. And again, to my ears, toroid just had a somewhat Spanish, so I went with the Spanish L, but of course it is just a toroid, the toroid, not El Toroid. So a toroid you can think of as similar to a solenoid, but kind of twisted back on itself to kind of form like a donut. So what we have, if I zoom in here, what we have is the current is going to run in the wire, and then we wrap the wire around, so the current is running through and around, through and around, through and around. And the magnetic field for the toroid will be analyzed using Ampere's law. And if you are asked to analyze it, you again, like the solenoid, want to think of just cutting it in half. So looking at the current coming out this outer portion and in the inner portion. And we are going to look at 3 Amperian loops. So we have an Amperian loop in what I'm calling Roman numeral region 1, so please put that in. A Amperian loop inside the core of the toroid, Roman numeral 2. And then we're going to have an Amperian loop outside of the toroid in Roman numeral 3. Well, this is a very short page of notes for us, and the derivation is very short because, as you can see, with region 1 and region 3, When we look at our I enclosed, we get no net I enclosed. First of all, there's no I at all in this region, in region 1, and in region 3, we have both the I out, and the I in canceling out. So I in and I out gives us no current in region 3. So we lose region 1 and region 3. We only have to analyze region 2. When we set up our Amperian loop in that inner portion, the only I enclosed is the inner I. So it's all of these I's, all of the I's in the inner portion. The current is going into the paper, so that's why I have negative here. My magnetic field from the IDL cross R hat, so convince yourself with an IDL cross R hat that you get the B field running clockwise as shown here. The Amperian loops, of course, by convention are counterclockwise, so we get a cosine of 180, which is nice because I get this negative and this negative will go together to balance each other out, cancel out. Our Amperian loop is now a circle again, right? The only exception to that is the solenoid. We have 2 pi r for our Amperian loop. So here we get the same result as the long straight wire, except we have the total current is the number of coils times the current in each coil. So same result where we get B field equals 0 till we hit the portion of the toroid. Now notice the B field in the toroid is strongest near the inner region, and then it drops off according to 1 on R, and then is 0 again outside of the toroid. And we can talk about what toroidal magnetic fields are used for in class, but at least you have the calculations in your notes and you understand the magnetic profile for the toroid.